Welcome, deep divers, to another intriguing journey on the deep dive. Today, we're tackling probably one of science's most famously perplexing experiments. You've definitely heard of it, the double slit experiment. Think of this as your shortcut to understanding, well, a really fundamental piece of quantum reality. And it's a reality where things just don't behave like you'd expect at all. We'll get into the bizarre behavior of light, of matter, and this century-old debate, a real clash of titans, Einstein versus Bohr. And then the really cool part, based on these sources, how a recent MIT experiment might have actually finally settled it. It's fascinating stuff. Okay, let's unpack this.
It really is. And what's fascinating here is this experiment, it's more than just physics equations, isn't it? It's like a direct window into the nature of reality itself. It's been a cornerstone of quantum mechanics for, gosh, decades now, always challenging our everyday common sense intuition. So our mission, really, in this deep dive is to pull out the key ideas from the sources you sent over, help you wrap your head around how something that sounds simple can just completely flip our understanding of what's real. Prepare for maybe a bit of a paradigm shift.
Absolutely. And to really feel the strangeness, let's just walk through the basic setup. Super simple on the surface. You need like three main things. First, a source, something that shoots out particles, could be light photons, could be electrons, one by one, ideally. Second, a barrier, just a screen, basically, but with two very thin parallel slits cut into it, like tiny twin doors. And third, behind that barrier, you need a detection screen. Think maybe old school photographic plate, something that shows where each particle actually lands. Okay, so classical world thinking now. If you're just firing tiny balls, imagine little marbles at this thing. What pattern do you expect on the screen behind it?
Yeah, I mean, common sense tells you.
Right. You'd see two lines, two bands, one lined up behind each slit. Simple cause and effect. The marbles that go through slit A land here, the ones through slit B land there. Straightforward.
Exactly. And that's where quantum mechanics just throws a wrench in the works. A big one. Because when you actually do this with photons or electrons and you send them one at a time, crucially, without trying to see which slit they went through, you get something completely different on that screen. Not those two neat lines.
Not at all.
Instead, you see an interference pattern. You know, like if you drop two stones in a pond. The ripples spread out, they overlap, they interfere. Yeah. Some spots get higher waves, some cancel out.
Peaks and troughs, yeah.
That's what you see on the screen. Bright bands where lots of particles land, dark bands where almost none land. And this is the classic demonstration of wave-particle duality. These quantum things, they can act like waves or like particles. And this is key, not both at the same time. Yep. It depends on, well, how you set things up.
But here's where it gets really interesting. Like, properly mind-bending. This interference pattern shows up even when you send the particles through one single particle at a time.
Exactly. That's the kicker.
How? I mean, if you send one electron, what's it interfering with? Itself.
It seems so. It's as if that single electron, somehow, manages to go through both slits simultaneously, like a wave.
As a wave of probability, maybe.
Precisely.
Yeah.
It explores all possibilities, and then it interferes with its own potential paths before it hits the screen and becomes a localized dot.
Can you even picture that? A tiny ball going through two different doors at once and then sort of bumping into itself? It just breaks your classical intuition, doesn't it?
Completely. It tells us a particle isn't quite the solid little thing we imagine, not until we measure it anyway.
Okay, so if that wasn't weird enough, the experimenters thought, right, let's figure this out.
Yeah.
What happens if we try to, if we put a little detector right by the slits to see, okay, did this electron go through slit A or slit B? Just peek.
And that's when things get even stranger, if that's possible. The moment you do that, the moment you set up any kind of measurement to determine the path.
The pattern changes.
Dramatically. The interference pattern, gone, vanished, poof. Instead, you see exactly what classical intuition predicted all along. Two distinct lines on the screen, right behind the slits.
Wow.
The particles suddenly start behaving like well-behaved little marbles again. They go through one slit or the other, but not both. The wave behavior just disappears. This is what physicists often call wave function collapse. Before you measure, the particle is this cloud of possibilities, this superposition. It could be here, it could be there, it could be going through both slits.
A wave function describing all that.
Right. But the act of measurement, even just finding out which path it took, forces it to snap into one definite state. It collapses from a wave of possibilities into a single particle-like reality.
Yeah.
And this raises an important question. Why? Why does simply finding out information, the act of observation itself, fundamentally change what happens at the quantum level?
It really does feel like the particles know they're being watched.
No.
Which sounds crazy, but...
It does sound crazy, but that's sort of the implication that rocked the physics world. And observation, by the way, doesn't necessarily mean a conscious human looking. Any interaction that extracts that which path information does the trick.
Okay, so this wasn't just some lab curiosity. This observer effect, this duality, it ignited this huge philosophical battle, didn't it, between Einstein and Bohr.
Oh, absolutely. One of the greatest debates in science history.
You had Einstein, Mr. Relativity, who just couldn't accept it. He deeply believed reality is objective. It's out there doing its thing, whether we measure it or not. This quantum weirdness, the randomness, the observer effect, he felt it meant the theory was incomplete.
He famously said God does not play dice.
Exactly. He wanted that underlying predictable reality. He thought quantum mechanics was just statistical, hiding some deeper hidden variables we hadn't found yet.
And if we connect this to the bigger picture, Bohr saw it completely differently.
Niels Bohr, yeah. Leader of the Copenhagen interpretation.
Bohr basically said, no, this is reality. At the quantum level, properties like position or path don't exist in a definite way until you measure them. The measurement process itself helps create the outcome. He argued you simply cannot separate the observer or the measuring device from the quantum system being observed. They form an indivisible whole.
So it wasn't just a disagreement about equations.
Not at all. It was a fundamental clash about what reality even means. Is it fixed and independent like Einstein thought? Or is it fuzzy, probabilistic, and partly defined by how we interact with it, as Bohr argued?
And the double slit experiment was ground zero for this whole argument. It just laid bare the core weirdness that challenged everything.
For decades, this debate simmered. Was there a deeper layer? Or was Bohr right?
Which brings us finally to the present day. Because according to the sources we looked at, there's been a major development from MIT. They apparently performed a version of the double slit experiment that's being called, like, the purest and most precise ever. A real breakthrough.
Yes, that MIT work sounds incredibly elegant. What they did essentially was use single atoms as the slits. Imagine that precision.
Atoms as slits.
Wow. Yeah, and they used very, very weak laser light, ensuring that each atom would scatter at most just one photon. Super controlled. And here's the clever bit. They could control the quantum blurriness, the uncertainty in the atom's positions. This allowed them to essentially dial in the conditions.
What do you mean, dial them in?
They could set it up so the uncertainty forced the light photon to behave clearly as either a wave, showing interference, or as a particle, revealing its path. But crucially, never both at once, just like Bohr predicted with complementarity.
Okay, so they could push it one way or the other, and what was the big finding?
The absolute key finding was this. Any attempt they made to gain information about the photon's path, even the tiniest, most subtle interaction that could potentially reveal which atom slit it went through, immediately weakened or completely destroyed the wave interference pattern.
No matter how subtle the measurement.
Exactly. Even the minimum possible quantum interaction required to get path information washed out the wave behavior. This, the researchers argue, directly contradicts what Einstein expected. If there were hidden variables guiding the photon, knowing the path shouldn't destroy the underlying wave nature so completely.
But it did.
It did, and it strongly supports Bohr's view. The outcome isn't predetermined. It genuinely depends on the type of measurement you choose to make, whether you're set up to see waves or particles. It showed the quantum relationship, the entanglement between the photon and the atom slits, was what dictated the result.
So the interaction itself is paramount.
Precisely. As Nobel laureate Wolfgang Ketterl put it, it was like a perfect thought experiment. Einstein and Bohr could only have dreamed of a century ago, finally realized in the lab.
Okay, so the verdict seems pretty clear then, based on this MIT work. The century-long argument. Bohr seems to have won the day.
The evidence certainly points very strongly in that direction. It reinforces the idea that observation or interaction isn't just passively revealing reality, it's actively shaping it at the quantum level.
It's quite a profound conclusion after all this time, a testament to experimental ingenuity, really. Right, so let's try and wrap this up. Let's boil down the core takeaways from this pretty wild journey. First, the double slit experiment is the absolute classic demonstration of wave-particle duality. Quantum stuff acts like waves or particles, depending on the situation, but never both at once.
Correct.
Second, and this is the mind blower, the act of observing or measuring which path a particle takes fundamentally changes its behavior. Wave pattern gone, particle pattern appears, observation shapes reality.
Yeah, the observer effect is undeniable.
And third, this recent MIT experiment using atoms as slits seems to have definitively settled the Einstein-Bohr debate, providing really strong evidence for Bohr's view. Quantum reality is probabilistic and influenced by measurement.
It really solidifies that interpretation based on incredibly precise data. And, the implication here isn't just some abstract physics concept that goes deeper. This experiment is fundamental. It touches on how we as conscious beings, or even just as interacting systems, engage with the universe. This raises an important question. If our interaction, our observation, alters reality at this most basic level, what does that really imply about the world we experience every day, and what's our role in it?
It suggests a less detached view of reality, doesn't it? More participatory.
Perhaps it hints that the clean separation between observer and observed that we take for granted might not be so clean after all, at least fundamentally.
Definitely something to chew on. So the next time you find yourself just, looking at something, maybe pause and consider the strange participatory dance of quantum mechanics happening underneath it all. It's a weird and wonderful universe. Thanks for joining us on this particularly mind-bending deep dive.